So in this video, we're going to do an overview of thermodynamics and how we can actually use the fact that by changing the pressure or the temperature of a gas, we can change the internal energy of a gas and then actually use that to translate that thermal energy into work or mechanical energy. So we first have to address the idea of closed versus open systems. So when we have a system that is closed, that is one in which energy cannot go into or out of. And when we have open systems, that is where energy can be leaving the system or going into the system. In this case, we're going to be looking at either adding energy in the form of work or heat into a gas, or allowing energy in the form of heat or work to leave a gas, and therefore change the internal energy of the gas. So the first law of thermodynamics is that the change in internal energy is equivalent to both Q, heat, and the work done. Right? So we have to distinguish clearly between the idea of work done on a system or on a gas and work done by the gas, right? Heat added to the gas, heat lost by the gas. So if we add heat to the gas, it ends up being positive, right? So it's going to positively change the internal energy of the gas, right? If we do work on the system, right? So if we are adding work, we make that a positive value. We're adding work to or energy to the system, that would also create a positive change in the internal energy. Remember that internal energy of the gas is equal to 3/2 nRT. So that's the number that we use to equate to the temperature that the gas actually is. So we have to distinguish between Q, which is heat energy, and T, which is the actual temperature. So we can actually affect the temperature of a gas in two different ways, by either exchanging heat or exchanging work. So if we are removing energy from the system, that could be in the form of heat loss, which would make this Q negative, or the actual gas doing work on its surroundings, right? So if we were to have a gas and it's trapped in some container and it expands that container, some force is being applied to the walls of that container and moving them some distance. So that is equivalent to work. So the gas is actually doing work on its surroundings. And so that would be form of energy that's going from the internal energy of the gas to, some outside of the system, to, the walls of the container. So we've already kind of looked at ideal gases and how they relate to pressure and volume and temperature. And in looking at like Boyle's law, we looked at pressure and volume graphs. And now we're going to look at what is called a PV diagram, and use that and the first law of thermodynamics to look at all of these different, how all of these different variables relate. So U and Q and W and pressure and volume and temperature. So if work is done, then some sort of motion occurs because of a force, right? So remember when we first learned about work, back in AP Physics 1, work is equal to force times distance. And we began in this unit talking about pressure and how pressure is force per unit area. So if I'm going to sub in for force here, pressure times area, then I would have that the change in work is pressure times area times the distance, right? And this would area times like distance that a piston might be moving. And again, I'll show you some images in a minute. It might make a little bit more sense. But you have then pressure times the change in volume would be equal to work, right? So let's look at a scenario of a PV diagram, which we say is isobaric. Iso means the same, bar means pressure. So isobaric means that there's no change in pressure. The pressure stays constant the whole time. So if we have a container that can change its size or has a piston that can go up or down based on the size or the volume of the gas, then we can actually see that change in volume and equate that to the work that is done. So again, we just looked and derived this equation that work is equal to P times the change in V. So if we had a PV diagram, we've been learning since the beginning of the year that area under the curve would be equivalent to whatever those y-axis times the x-axis is. So area under the curve in this case would be work. Now we would want to think about it in two different directions, right? So we have this end of the curve, and if we were to go from here where we have a low volume to here where we have a large volume, that means that the gas is expanding within the container. So if the gas is expanding, the gas is actually exerting a force on the piston, causing the piston to move. So this would be a scenario in which work is being done by the gas on its surroundings. So that is internal energy that is leaving, right? However, if we think back to gas laws, if pressure remains constant, but the volume is going from something low to something high, then how has that happened? It's happened by increasing the temperature. So we know the overall internal energy of the gas must have increased because the temperature has gone up. And since work is being done by the gas on its surroundings and work is going out of the gas, then we must have added a bunch of Q heat in order to follow the first law of thermodynamics. So we know that work is leaving, right? So work is going out. So that's going to cause the internal energy to decrease. But because the volume's bigger, we know it's hotter. So really overall, this change in internal energy has to be positive. So if this number is positive and this number is negative, that must mean this number is positive. So we've added a bunch of heat to the system. Oppositely, if we think about it from going from a large volume to a smaller volume, then again, we would be looking at the work being done on the gas. So we're adding energy by the piston exerting a force and making the volume smaller. And then heat would have to have been lost. Heat would have to have been lost for the change in the internal energy then to be going down. Now, we also have a scenario where we can look at PV diagrams that are considered to be isochoric. So iso means the same, choric means volume. So here we can see that this line is straight up and down, where the pressure is either decreasing or increasing, but the volume of the container is not changing. When we have a straight vertical line like this, there's no area under the curve. So actually the work is equal to 0. So this value would be 0. And, but we do know that the pressure is changing, right? So the pressure is high here, or the pressure is low there. And so because volume is fixed and pressure is increasing or decreasing, we know that pressure and temperature are directly proportional to one another. So that means that if pressure is increasing, temperature must also be increasing. So to apply that then to our law of thermodynamics, if temperature is increasing, the change in internal energy is increasing. And since work is 0 in an isochoric system, that means that the way the temperature is increasing is by the addition of heat. Now we also have scenarios where we see something being isothermal. Isothermal means the same temperature. So that means that there is no change in temperature and therefore there's no change in internal energy. So that means that this value would be the same. So as whatever amount of heat is exchanged out of the system must be equivalent to the amount of work going into the system. So whatever form of energy is being lost, we must regain that energy back in some form. So this looks like a curve Here, this is what an isothermal graph looks like. And just keep in mind that along an isothermal graph, every point in this line, the temperature of the gas is staying constant. So we've looked at a situation where we have the same pressure. We've looked at one where we have the same temperature. We've looked at one where we have the same volume. Now we can also look at a last scenario where we have something considered to be an adiabatic process. An adiabatic process is one where there is no exchange of heat into or out of the system, right? So remember isochoric, when there was no volume change, that's where we said that there was no work, right? Now we have this scenario of like, okay, well, what if there's no Q, right? So we can't, an adiabatic process is when something is perfectly thermally insulated. So no heat energy can leave the gas or come into the gas. So that means any temperature change that happens within this sort of system is all equivalent to work being done either on the gas or by the gas. Now, some practical examples of how we use this changing pressure and volume in order to translate it to the movement of a piston and therefore mechanical work would be in a combustion engine. So this demonstrates the strokes of a combustion engine where you have gas and air that come in, and as they come in, they force this area to expand, which moves the piston down, and the piston then moves down and cranks around. And then just by momentum of this swing, the piston moves back up and compresses the gas, which exerts a force onto the spark plug, igniting the spark plug. So you have this little explosion, which then heats up the gas in there. The volume expands, causing the piston then to go down this way and then swing back around and then forces gas out of the exhaust valve and then pulls gas in to start the whole process again. Right. So the PV diagram for an engine, the two strokes of an engine is here, and you can kind of see we can plot the pressure versus volume over time and then get that work or that movement of cranking that piston in order to translate that into some sort of torque or movement within the car. The second law of thermodynamics we've already mentioned when we've looked at calorimetry and the movement of heat. So the second law of thermodynamics says that heat always flows from hot to cold, which is a result of the collisions of adjacent particles. So when particles are moving and they collide with one another, they transmit their kinetic energy from something that has a lot of kinetic energy to something that has a less amount of kinetic energy. So using this idea of movement from hot to cold, this is how we can use heat engines or steam engines. So we have one temperature vessel that is very high and another that's low, and the difference between the heat here, we can force some sort of gas to move from an area of hot to cold, and then as a result, that change in temperature from the hot to cold, we can actually harness that in the form of work. So if we look at a little bit more of a practical application of this, here you have a boiler. We create some steam, so it's really high temperature up here. We have a chamber here in which we have a piston that can move as gas moves into or out of here. And so the gas comes down, it's hot. We want the hot air to move towards the cold air, naturally does this. And then we have a chamber here which can expand, which then would move a piston, and then it cools and then warms. And so we create a cycle. Same thing here, we have a high pressure steam and a low pressure steam, and we can spin a turbine. So efficiency of an engine can be calculated by just taking the amount of work or energy we get out mechanically and comparing it to the change of heat. So it's really just a percentage. We can also calculate like the Carnot efficiency, which we say is looking at the temperature difference from one to another and then trying to figure out the maximum. And we'll do some of those examples in class, but hopefully this gives you enough of an introduction to thermodynamics that we can start getting working on some problem sets.